Today I'm going to talk about some off-critical dimer models and their connection with massive SLE2. So we've had quite a lot of SLE, not that much dimers yet, but my talk will follow that direction. It'll also be more about SLE than about the dimers. This is based on joint work with Markarov and Smirnov. It will also be here next week. Okay, so what's the dimer model? So we have some finite graph, and the dimer configuration is what you see here. That's the dimer configuration. So it's a collection of edges such that every vertex is in exactly one edge. And so if that's such a configuration, and we're giving a set of weights on the edges, then we can assign a weight to such a configuration by just multiplying the weights of the edges. And then we, as we've done many times this week, we sample a configuration by dividing the partition function. Now we have a probability. So what you see up here is just that for the hexagonal lattice, which will be my lattice of choice for this entire talk, you can kind of see it nicely as a stacked picture of boxes, also like a surface. So here's the big picture. So this is kind of like really this is a summary of some things that has come before. So if you have timers with uniform weights on certain pieces of lattices, so this is not general. In particular, it will mean, for people that know something about it, that I will have flat boundary condition. Then there's a bijection to a uniform spanning tree on a different called Temperley bijection. And a uniform spanning tree I can sample by using Wilson's algorithm on something called loop-erased random walks. And so this is a very nice combinatorial property of these things. And what is nice about this picture is that all three of these things have scaling limits. So the arrows tending downwards have scaling limits. So here, this, you first need to encode your dimer configurations in a height function. I will not say how to do that, but it's in the picture. So before, it's kind of this image that you saw on the right, the three-dimensional. And then it will converge in this setting, because I have flat boundary condition, to a GFF. GFF has appeared on the plan. Then the tree also has a limit. And that is a continuous random tree. And the loop-erased random walk has a limit, which is called the certain SLE2. And so the connections above, the Temperley bijection and Wilson algorithm, they in some form survive this. So this one survives very clearly by saying a single branch of this tree has the law of SLE2. This one, maybe one could say that's a bit, this is a bit vague, the winding, but this will not be the focus of the talk. Focus of the talk will be on the right-hand side. So what I said now, this was all known before, and so I first wanted to say what is a loop-erased random walk. Okay, sorry. So a loop-erased random walk, I just said it, but it's what it sounds like. We start the random walk at some point in the domain, we run it until it hits the boundary, and then we erase the loops as they appear. So we will get a simple path from some point to the boundary. If we had not erased the loops, in the scaling limit we would get binary motion, and so on this side we kind of see already there's if you had all the erased stuff, it would be kind of a binary motion from the origin to the boundary. But since we erased, we get something else. And this is proved by Lawler, Schramm, and Werner to be SLE2, the scaling limit. In particular, also in this triangular case that we're here, but also in the square grid. And these are now theorems for the other two convergences. The tree converges to a scaling limit, and the height function converges to Gaussian field. These are not the only theorems in this field. There's lots and lots. This has been proven in different settings, and you can see that these are not maybe the strongest theorems. Like here, there's just the scaling limit exists, the scaling limit has not been described, and so on. And here, this is also has been proven in much more general settings. There are some examples. But I want to get to what I did. So here, what we're going to do is the things I said now were for uniform weights, or at least for some specific weights on the edges here. And we're going to put some different weights. Also not general, but some specific different weights. this thing will still work. This is not really about the weights, it's about the combinatorial. So we just get a spanning tree also with some weights, and then we will get a different random walk here. So this step will also work. And then the important thing is, what is this random walk here, and what is its loop erasure, and what is the scaling limit of the loop erasure. So what weights do we put? On the hexagonal lattice, we put in this kind of doubly periodic way, we put weights until on these points. But we will not actually choose them doubly periodic, it's just here on these points we can put some weights, and the other edges need to have weight 1. But these A, B, and C, they can depend on the vertex. So we will have, the important thing is that we have some weights that work well with the Temperley projection, and they depend on the location. So, and I said what we had until now was they are all equal to 1. And it turns out that if you just fix other weights, especially if they are for this kind of bounding condition, you will get a weight that is in some sense trivial, like for this specific setting. And to get something interested, we need to move our weights to be close to the critical point as we let our mesh size go to 0. So we will have a scaling limit. So the edge length here will be delta, and this ABC that I put here, they will converge to the critical point as delta goes to 0. This is kind of analogous to the question.
So A is 1 plus D0, B is 1 plus D1.
Yeah, I think, I hope maybe later the left side actually A1, A2, A3. Okay, or I0, okay. Yeah, good point. This was a bit inconsistent with what's here. And this is another.
Is there a reason why this scaling is the one where you see something?
Yes. So, for example, if you already have this picture in mind, then you can see that this scaling is exactly the scaling, such that the random walk will converge to a non-trivial limit. It will converge to a Brownian motion with drift, some STE. So that's actually okay. So we had this in the Temperley projection. This is the graph we get. There are 3 lifts, so it's a directed triangular lattice. So all the edges have been directed either to the right, to the top left, or to the bottom left. And this is the graph that our random walk will also live on. So we get a random walk, namely this one. And so here is the ABC. So our random walk has these transition probabilities. So now I put a 1/3, so the transition probabilities, but you can do this because there's a certain gauge invariance. So earlier I had 1, now I have 1/3, but this is not important. So this is a random walk, and if it's a position x, it will have certain probabilities to move into one of those 3 directions. And we want to, this is the random walk that we need to take a loop erasure of, and then a scaling limit. And we will do so by connecting it to another random walk. This other random walk takes a step into those 3 directions with equal probability, but the probability doesn't quite sum up to 1. And with the remaining one probability, it will just stop. This is called a random walk with mass. And so I will now explain how to connect these 2 random walks, and then how we can use this to find the scaling limit of the loop erasure of the random walk on the right, and connect this to the scaling limit of the loop erasure of the random walk on the left. Okay, so I will explain the connection of these 2 random walks, first by going to continuum and explaining the connection between the continuous analogs. So if we go to the continuum, then the random walk on the left, if we assume that these A, B, and C scalars on the previous side, and approximate some continuous, like smooth enough drift function, then we will get this scaling limit of the walk on the left, solution of an STE. So there's an STE, so that's dxt, and there's the drift, and then there's the Brownian motion. So, and it will be an assumption on our A, B, and C that they are such that this holds, that we have such a scaling limit. And then we can write down its Radon-Nikodym derivative with respect to regular Brownian motion. So here I write it down if I run it until time t, and I compare the two, and I've given some specific path, how much more likely is this for random Brownian motion with drift as compared to Brownian motion. And you get this. So this looks probably kind of familiar. I hope I checked. Yeah. So well, it's easy to mess up the factors here because it's 2D and usually white is in 1D, and then, but I think it looks very, very bright. We need to watch out for this invariance of your 2D Brownian motion. Let's just ignore factors for now. Yeah. And then what's the scaling limit of the thing on the left? So here it's just you kind of just die at the rate that is given by your position. And so if you assume that this is scaled correctly, which will actually look slightly different, so this rho x needs to be of order delta squared, then this will kind of converge to a regular Brownian motion with a clock. Like a clock that rings at a rate that depends on your current location, and if it rings, you kind of stop the walk, and then it doesn't contribute to your measure. So this is now a sub-probability measure here. So, but it assigns to a certain path the probability of still being alive. So this is sub-probability measure. We can make it into probability measure by maybe conditioning on something, on staying alive, but until you hit a certain boundary, for example. When you get something non-trivial, that's a probability measure. But here for now, it's fine to just work with a sub-probability measure and look at this. And now the two can look already kind of similar. So there's this term here. We can see that it's exactly of the shape as this. But this stochastic integral here is quite different. So we need another assumption that will allow us to connect the two. And this assumption will be that the alpha is given as the gradient of something. So if alpha is the gradient of something, then we can use eta to write it like this. And now our Brownian motion with drift will be given by, the Radon-Nikodym derivative is given by something that depends only on the end and start point. And if we fix x0 to be the origin of something, it will only depend on the end point. And something that looks like a drift term. Which leads us to our final assumption. This drift term, like what's written here, it should be positive, because it only makes sense to die at a positive rate and not a negative rate. I actually personally think that maybe one could try also splitting so that you die at a negative rate. But for now, our paper is it's just you only die at positive rates, so we need to assume that this is positive. So our assumptions of alpha is that alpha is the gradient of something, and this function here is positive. And if we have that, then we can see that the Brownian motion with drift and the Brownian motion with this mass are related. And if you look at kind of the ratio of their Radon-Nikodym derivative, you see that it's only a function of the endpoint of your path. So in particular, if you have some domain, and the start point, and in here you have this alpha drift field which is given by a function, and you run your STE until it hits the boundary, and you condition on it hitting at a specific point. You say I condition on hitting here. This makes sense, at least if the boundary is nice enough, or if you're actually still in discrete. That makes sense. Then this law is actually the same as if when you run a massive Brownian motion until it hits the boundary, and you condition it to leave here and survive until doing so. So we see that after conditioning on the exit point, our Brownian motion with drift and our massive Brownian motion are actually the same thing. And now, we don't want to do things, this is already quite interesting in a way, but quite elementary. Now the important thing is that this, I can do all of this also in the discrete. And this is not obvious.
Sorry, so what is the intuition? Is like the Brownian motion wants to avoid the places where it would get killed with high probability in some sense?
Yeah, the intuition is that if you have a drift field and it's the gradient of something, so it doesn't point inward or outward, it basically points in some direction. Like locally you can think it's constantly pointing in one direction. Then it's kind of the Brownian motion doesn't want to go in circles yet. It doesn't want to stay here long. That's kind of costly because it needs to go against the drift and again. And somehow going against the drift costs you more than going with the drift gains you. You can kind of think of this, I don't know if you have like a random walk in 1D, like if you compare the simple random walk, you go back and forth, you go 1/2, this costs 1/4, but if you have if you go 1/3, 2/3, back and forth, this is 2/9, this is less than 1/4. So staying in the same place is something that the one with a drift to the left, in this case, wants to do less than the one without drift. And so you can kind of see that if you have a very strong drift to the right, and you condition on exiting here, the way to do it is quickly. You don't want to hang around, then you have to fight the strong drift to the right very long, and then you still have to go here. You want to do it quickly. And if you have a mass, you want to exit quickly anyway. So that's.
Just to be sure I understand, if now you want to go towards the drift, then you will be very comfortable here.
Yeah, but that makes sense also. Like if you condition on going somewhere here, then the drift will do it quick throughout and the standard Brownian motion, and the massive one also will do it quicker than standard Brownian motion. So it's kind of makes, yeah. I think this is, yeah. And so doing this in the discrete is actually one of the reasons why we are on this funky directed triangular lattice. Because when we define the natural analogs of a gradient and a Laplacian on this triangular lattice, we can find that here it will be a discrete path. So gamma is now a discrete path, a sequence of edges. We actually find that we have the same Radon-Nikodym derivative that looks like a discretized version. Okay, this beta is a bit ugly. This beta is actually the term that we should, but it's important thing here is that it's like a mass. It's like a function of the vertices, not a function of the edges we go along. So here we see that in the discrete we can show that this is the same, and this would, for example, not work on a square lattice. In a square lattice, you need to kind of say that this is true on average. Like if you take, if you look at all paths, discrete paths that are close to some continuous curves, and you look at the probability to be in one of those paths for the non-drifted one and for the drifted one, then this should then also give you this, but it's not true path per path. And this is it's a nice coincidence that the thing that you get from the Temperley conjunction when you start with the hexagonal lattice has this nice formula. So we did this also for constant drift. So alpha is just a constant on the square lattice. So there we proved it, and because of this I'm convinced that you could do it also in the general case on the square lattice or on an isoradial graph or something like this. But it works very nicely in the triangular lattice. So let's not worry too much about it. And why is it important that we can do this in the discrete? That's because you can't really take the loop erasure in a nice way of the continuous object. If you have a Brownian motion and you want to erase its loops one by one, you have the problem that you don't know where to start because it makes infinitely many loops right in the beginning. And so there's some sense in which still SLE2 and the Brownian motion can be coupled so that the SLE2 is like the loop erasure of the Brownian motion, but it's not direct and it's not easy to use it. So it's much nicer that we can do this in the discrete, and so we can say also that the loop erasure of a random walk with drift, conditioned on the exit point, has the same law as the loop erasure of a massive random walk, conditioned on the exit point. And for that, we needed this in the discrete. Okay, so that's what we have. No. So what do we need? We need a random walk with a drift, which corresponds to a continuous thing of a gradient. So this is not a discrete gradient, so this is discrete. So it's a random walk with a drift given by a gradient, and a walk with a corresponding mass. So the mass, you had this formula earlier, this is Laplacian plus norm of gradient squared. And you run both of them until you get a plane. You assume the mass is positive, and then if you condition the x point, the laws are equal. It's also the laws of the loop ratios are equal. And then, if we can combine this with the following, namely the scaling limit of the loop ratio of the massive random walk on a triangular lattice is massive as V2, then we have identified the law of the scaling limit of the loop ratio of the recent walk with drift. So we need the two components. We have the connection of drift and mass in the discrete, and then we have the scaling limit of the massive one. Okay, so what about the scaling limit of the massive one? What should it be? Okay, I skipped my definition of SLE. No, usually in this talk I have a definition of SLE in the beginning. You've seen it so much this week. So now, massive SLE, I guess I still need to define here. So you take the Löwen equation, this is the radial one. We've seen the caudal one more often, but it works essentially the same way. It's just that this one is the SLE, where you grow an SLE inward towards a target point that's in the domain. And if you didn't have this lambda ddt here, then it would just be a regular radial SLE. And massive SLE, it just has a drift term. And the drift term depends in some quite non-trivial way on the domain that you've already seen. So I'm not going to explain exactly what this here means, but rather I'm going to focus on an alternative description is that a massive SLE is a random curve for which certain things are martingales, and the certain things are related to the martingales of regular SLE, but they're not the same. So they satisfy they are, instead of being harmonic, they're massive harmonic. So I'll go into this. I think I have like 7-8 minutes. Yeah, so I think I will not skip the slides about this, so I don't need to say it now. So, yes, so it's a thing. It was proposed by Markarov and Smirnov to be a scaling limit of a number of models that work like the thing we saw here. You have a critical model that converges to an SLE, and then you change some parameter somewhere slightly in a way that goes to 0 as the scale goes to 0. So the way that goes to the critical value. And then, if you turn it right, you will get something that inherits some of the structure, is in many cases still absolutely continuous with respect to the critical thing, but now depends on an additional function, for example here the mass. So, yes, what do we prove? So, that massive loop restaurant block converges to massive SLE2 was first proved by Jacob and Van for the square lattice, and we just needed to generalize this because they proved it for constant mass and for square lattice, and we had a different lattice. So I think if we had tried to do the minimal thing, it would not have been that different from what they did, because we needed to generalize anyway. We proved a significantly more general thing because we proved it on a graph satisfying some assumptions, but I don't want to go into how, and then we check those assumptions for the triangular lattice. So you can see in the paper we have now. We did this in particular using an idea from Yadin and Yehudov, where they proved under very general assumption on a graph that the loop ratio of a simple random walk, or like any random walk that converges to point in motion, basically is SLE2. So we used ideas from Yadin and Yehudov. And the important thing is these massive martingale observables. So what are they in this case? In this case, they are the limits of the, what we call the massive Poisson-kernel ratio. So here, what is this? This Z rho is a partition function of all random walks that go from x delta to a delta in the domain omega delta t. So here x is in the interior and a delta is on the boundary. So if you divide this by, let's say, all random walks that start at x and leave the domain, so all paths, then this will be, that would be the probability to leave for a delta. And this rho here is our mass profile. So this is the random walk path. So this is kind of a Poisson kernel, and then we divide it through a reference point O, and we see this whole thing as a function of x. So this is what was done in the non-critical case. You don't have the rho here, and then you can easily see that this is harmonic, and that's important. And you can also see that this is a martingale.
This is a massive Poisson kernel. This is for the unconditioned massive walk.
Yes.
The condition is to survive all the way to the boundary.
So here, this is for the unconditioned, so it will be less than 1. Yeah. And so, and this is a martingale in T. So if we evolve our domain, we remove one of a domain. As long as the curve doesn't get close to either the target point O or the point X, this will be a martingale. So we will stop it when it hits like a ball around either of those. Or actually what you often do is you assume that X is in a ball around O and you stop this once you get to a ball that's slightly larger. And so, still in the massive case, this is a martingale. So this survives very directly. And this will no longer be harmonic, but massive harmonic. So you can, in a continuum, this means it will not satisfy Laplacian of P is 0, it will satisfy Laplacian minus rho, so like the operator that multiplies in every point per rho of x of P. This will be 0. So, and that is in general, like that's a general fundamental thing about massive SLE, is that you have something that is a martingale with respect to your curve going, and is harmonic for SLE, and for massive SLE, the thing that satisfies the same boundary conditions, but is massive harmonic, will be a martingale. So in some sense, this is also a definition or a characterization of massive SLE. And so, what's the hope? The hope is that you can prove that this converges to continuum limit. There's a continuum limit. Then, most of the time, because you can kind of stop, it's not too hard to see that if you can prove this, the continuum limit will also be a martingale. And then, if you know that the continuum limit is a martingale, you can use this to determine what the drift of your driving function must be. And then you can identify the law of this, and then you can see that it's massive SLE too. So that's what we did. So you need you need to know some things about this limit, and these things are given by so-called resolvent formulas from Markarov and Smirnov. This is already the important thing about this is that it allows you to connect the massive thing. There should not be a rho here. There should be a 0 here. To the non-massive thing. So we have this massive kernel, and with the massive clean function, we can connect it to the non-massive thing. And we also need to prove this. Okay, now I'm going over time, so let's just say we know some stuff about this continuum limit, we need to prove some stuff, but once we prove that stuff, this being a martingale is enough to show that lambda t is the thing that clean limit is. Okay. So let's get back to this big picture very quickly. So we now spent a lot of time here. We were then able to connect the localized random walk of drift to a Schramm level equation with mass. And the question is, of course, can we also go back here? So the tree, it still makes sense, so in some quite strong way. The tree is determined by its branch law in a way, at least in the right topology. So this makes sense, even though it's not too easy to say anything about it.
Is it, so the tree is absolutely continuous?
That's not clear.
Right.
That's not clear, and we don't know. It's a good question. If this tree is absolutely continuous to the one you get with SLE2. I think the reason we believe that it is true is because Nathaniel has now a new project on this. So let's go here. So there's a conjecture. And one theorem here, because people told me that it's quite far along. So, but I put a question mark because also.
I think you will talk about it next week.
Yes, I want to say, if you want to know what the actual status is, you just need to know about it. Wait until next week. Nathaniel will talk about it, and I guess he will tell us what the status is. I am not part of the project, so I can only tell you about the conjecture really. The conjecture is that this, the scaling limit of the thing will be something that is, you can write, at least formally, as a reweighted Gaussian free field. So here you take a Gaussian free field. And then here, this, like people are confused about the way we write this, maybe it's not the best. So we're identifying alpha as like a 2D vector. We're identifying those with complex numbers. And so you can take this as an inner product either in R2 by identifying this with a vector, or it's like this, it's like the real part of this times this conjugate. Not that important. The important thing is, if you take alpha constant in one direction, this is the sign-Gordon field. Because then this is just cosine of square root beta h. So it's the sign-Gordon field at the Frank-Fermion point. That's our conjecture. And then, like, for alpha pointing in another direction, then here you just have like something like a phase shift. But for variable alpha, this is kind of a new field. Yeah, and there was some progress in Scott Mason's paper from 2023, where he proved this on the level of 2-point functions in the full plane. But the theorem here is going to be in a finite domain. So that's what I can tell you. I'm not entirely sure for which alphas they can get it, so you'll have to wait until next week. Okay, now some open questions. So don't need to do this too. So we have these conditions on the alpha, and I feel like on some level there should still be a scaling limit of the loop ratio if the alpha doesn't satisfy either of those. So I think the first one is probably quite difficult because it seems like if you make it more likely that the alpha makes it loops, it seems hard to say something about the loop ratio. I think non-positive mass is doable by connection to like branching processes. But it's also like there's some issues in like defining what the continuous limit is supposed to mean for non-positive mass. And then the last one is that there's for SLE4, it's like Leonie's paper, that connects massive SLE4 very cleanly with the massive GFF. But in general, for any kappa, there's like the flow line story with GFF and SLE kappa. And so it would be interesting to see if one can still get something with massive SLE2 and the massive GFF, or if it's really the case that like the massive GFF is the wrong thing to look at, and we should look instead at this field.
If everything in the big picture commutes, like shouldn't this mean that massive SLA2 are the flow lines of this sign-Gordon type field?
Yes, definitely. And I mean, this sign-Gordon type field, I think there's some, like, one can see that it's somehow not too far from the massive GFF. I think.
I think if I have to give my opinion, I think in the massive GFF won't be the same massive SLE2.
You think it's a...
Yeah,
so...
like it will be another massive version of
That's also a story I've not talked about. There's, for every SLE kappa, there can be multiple things that are called massive SLE kappa. So there's not just one, there's a one parameter family of them. So it could be that the flow lines of the massive SLE2 are just not...
The massive GFF.
The massive GFF are just not this massive SLE2, but a different massive SLE2.
Presumably you can guess what the martingale observable should be for that version of massive SLE2.
Yeah. Yeah, no, it's definitely like. Yeah. So I feel like I've had this question here for now, and even though we don't like have a good answer, it seems like we're getting closer to understanding more and more of the story. So maybe soon. Okay, no, just the efforts. Okay, thank you very much.